anyway, you know, remember that a class like that has been recorded in previous semesters. You will be able to, you know, you will be able to watch a similar class that was recorded previously, okay? Let's see, now we're recording. Pause, yeah, now you're recording. Okay, so again, today is September 26, 2022. I failed to record the class from the beginning, right? So we're starting to record right now. If you need to review this material that I cover up to now, operations between vectors, right? Vectors and operations between them, you can look at the videos of the previous semester that I posted there in my YouTube channel, okay? And thank you for reminding me, Lydia, yeah? You know, I made this mistake, right? I thought we were being recorded, but we're not. Now, let's take a little break, right? But before you go for a break, let's take attendance. Very soon, you're going to start doing some numerical work with those vectors. So far, we just did some graphical work. This graphical work is very intuitive, right? It's easier to see figures than to see mathematical numbers and mathematical letters. Okay, so let's take attendance right now. Attendance and today is the 26th. Jade, are you there? Jade, let's see. Yeah, Jade is not here. Vanessa, are you there?
Here.
Thank you. McKean? Thank you. Ashley? I see Ashley here in the list.
I'm here.
Okay,
Sorry.
good. Fisher? Dawn?
Here.
Thank you, Fisher. Blessing?
Here.
Erica? Erica with R, right? Not with L. Okay, so doesn't look like
I'm here.
Who is that? Is that Erica with R or Erica with L? Okay, Erica Pajardo. Okay, good.
Yes.
Yeah, okay, good. Thank you. Janet Garcia.
I'm here.
Thank you, Janet. Raymond Garcia. Raymond. I see Raymond. Okay, good. Thank you, Raymond. Donovan, I don't think it's here, right? Donovan not here. What about Lily? Lily, I don't think she came in today. Yeah, didn't come in today. Michael didn't come either. Wendy Hernandez. I don't see Wendy here in my list. Joshua Jimenez. Are you there, Joshua? I don't see Joshua either. Bethany?
I'm here.
Thank you. Luis Latiza. Luis, I don't see Luis here. Are you there? Nope. Ana Lopez. Are you there, Ana? Nope. Basilio Lopez. I see. Good. Thank you, Basilio. Bahag.
Here.
Thank you. Daisy Mariscal. Thank you, Daisy. Alejandra Marmolejo.
I'm here.
Thank you. Amarilis.
Here. No, really?
Julissa not here, right? Let's see. No, Julissa is not here. Yesenia. Thank you, Yesenia. Mary Okeki.
I'm here.
Thank you. Ryan Ong.
I'm here.
Next, thank you, Ryan Arthur Pacheco.
I'm here.
Okay, next is Jennifer Perez. Are you there, Jennifer? Okay, I don't see Jennifer here in my list. Labeled. Labeled, I see her in my list. Okay, thank you. Labeled. Lydia Rosas, thank you. Pedro Ruiz, I don't think he's here. Donia?
Here.
Thank you, Donia. Elika Lafay.
Here.
Thank you. Brianna Valencia.
Here.
One more. Mia Villalobos.
Here, Professor.
Thank you. Justena.
Here.
Okay. What about Arika Price? And Kelly Tabuhara. No, right? So we go. Good. So we have 25 here. Okay, good. So it's 9:47 right now. Let's go until 9:57, 6:02, right? Break till 6:02. No, 6:02. What do I mean? 10:02. Why I'm saying that? 6:02, right? 10:02. Break. Okay. Break you 10:02. Okay. Okay. Any questions? Okay, so we can go for our break now, and I see you in 15 minutes. By the way, I'm gonna pause the recording so the file doesn't get too large. Remind me to turn on the recording when we come back, okay? Okay, I'm back here. I'm recording now. So what I want you to do, when you go home, practice summation and subtraction of vectors using both the head to tail and the parallelogram method. Just make up your own exercise, right? And practice the procedure that I spelled out for you. And practice the procedure I spelled out for you. Here. Okay. So don't forget, what we did so far is just a qualitative way, just a qualitative graphical method to sum and subtract vectors. Okay. So what we're going to see next is the use of semi-quantitative methods to get the actual numeric value of a vector. Okay, so here we go. We don't need that anymore. Okay, I like this method. This is a way of mathematically determine the resulting vector when you sum two different vectors. Okay, so here you go. We can write vectors in terms of its component. What do I mean by component? vectors are two-dimensional entities, right? Even three-dimensional entities. Let me see here if I can get that for you. Okay, here you go. Vectors are two-dimensional entities and even three-dimensional entities. So when you come up with a vector in the two-dimensional space, let me write that down here. I don't want to overwhelm you with so many stuff, so many things here. Suppose that we have this original vector here, A, right? Even better, I'm going to show you something even simpler. Okay, we have this original vector right here that makes an angle theta with the horizontal. Okay, so think about that. Let me get this. The horizontal would be this one right in here, and I'm not even going to put an arrow there. Okay. So what we can do, we can express this vector in the Cartesian coordinate space. We first put the x-axis that we already had there before, and the y-axis, okay? And put the origin of the coordinate system at the tail of the vector for now. And what else can we do? We can do the following. We can break down this vector like it is its x component. Okay, just like I did here. Can you see that? I'm projecting this vector along the x-axis. And I can also break down this vector in terms of its y component. And I represent the y component as a vector, right? A vector with this y subscript. The x component as a vector A with this x subscript, right? Having said that, let's see if I have, I can state that this resulting vector A is what? Is a sum between those two vectors that lie, between the vectors that lie in the x direction and the vector that lie in the y direction. Make sense? See that? Head to tail method, right? Tail of the first vector starts here, comes here, and tail of the second vector is placed at the head of the first, and the sum of those two results in this other vector right here. Okay? So every vector can be broken down in terms of its component. That's what this thing is all about. That's what this story is all about. Okay? We can do also for the B vector. We can do exactly the same for the B vector. Bx and by. Suppose that we have the second vector B, right? We can break it down in terms of the bx and by components. And then we can also sum up those two vectors. Look, now we have a mathematical way of determining the resulting vector C, which is A plus B. Okay? Here you go, capital C. What is vector C? Vector C is going to be the summation of A to B. And by the way, the x component of C is going to be the x component of A plus the x component of B. See that here? The summation right here. And the y component of C is going to be the y component of A plus the y component of B. We're going to make a numeric example very soon, so you understand better. So we have, let's see if we have, yeah, I need one more slide here. I'm going to translate this vector C sub x right here, okay? Now we don't need that anymore. We don't need the AY, we don't need the BY. We do not need the AX and the BX. Okay. And look what we get. Right? We have just a regular summation, right? You can do the head to tail method, or you can do the parallelogram method here. Okay. The parallelogram method will result in this vector C that you see right here. Okay. Let's do a numerical example now. Let me see if we have more here. Okay, that's another way to picture that. Okay, that's the vector X. That's the vector A. The red vector is the vector B. And then we have the X and Y components, right? And then when you sum them, you end up getting that vector C that's longer. Those are the two-dimensional vectors. The three-dimensional vectors we illustrate like that. Can you picture that? Okay. It's difficult to draw those, to draw something in the three-dimensional space to appear, right, in the two-dimensional paper, right? It's difficult to do that, but we can give it the illusion that this vector here is in the three-dimensional space. Just like we have software that do that for us. See, we have the vector A. This vector, let me write that down. Here you go. This vector A that has components in the X, Y, and Z axis. That's the X component of the A vector, right? I drew my three-dimensional axis of coordinate axis, just like that, X, Y, and Z. Here you go, that's the AX, that's the A sub Y. This vector that you see here is the summation of AX plus AY. Okay, that's why I illustrated as being AX, A sub XY. And here's the Z component of the A vector. The A vector is the summation of this component here plus this component here. Okay, what else? Let's do some examples. So you can numeric examples now. Okay, so let the A vector be 2x. Oh, by the way, there's one more thing. There's this notation here. That this is another notation, okay? We can define, to make things simpler, we can define a unit vector that lies along the X, Y, and Z axis. Let me illustrate that in the let me see if I did that here. Oh yeah, here you go. I illustrate them here. Okay, I can define, you know, arbitrary vectors, arbitrary unit vectors that lie along the X and Y axis. Okay, so let's say we have this little vector pointing along the X axis that has a unit 1, that has a length of 1. It doesn't have any dimension whatsoever. Okay, X, and we usually those unit vectors, we call them X hat. Many books call this vector not X hat, but I hat. And then we can define also a unit vector along the Y axis. And we put this hat there at the top of the letter. The hat means 1, unit of 1. Okay? When we do something like that, we can here write our A sub X vector in the same way that we wrote there in the notes. Okay? Can you picture that? Okay? Picture a unit vector that we define along the X axis and another unit vector that we define along the Y axis. So now, with this definition, which is very useful, by the way, right? I'm going to write it down here. Here you go. My A sub X vector can be written down as being the scalar component a sub x can be either negative or positive times the x hat vector. That's what we did. It's very convenient to do that. Similarly, the y component vector can be written down as the component, the scalar component of this vector times the unit vector y along the y direction, y hat along the y direction. Okay, and like I said, it's a very convenient way of writing vectors. And let's do an example. Okay, many books, like I said, many books, especially at this level, instead of calling the vector x hat, they call it the vector I hat. So if you have x, y, z, instead of x, y, z, the book calls I, j, k, okay? J. So let's see. And I can even do for the z component as well, right? If you have a z component, if this vector has a z component as well. Here you go. Instead of j or I, we put a k here. I prefer this notation here for x, y, and z, okay? X hat, y hat, z hat. For some reason, people introduce this notation, I, j, k, in undergraduate work. I do not know why they do that. And then later on, when you go to graduate school, they switch from this notation to this notation, from I to X, you know, I, j, k to X, y, z. I don't have a clue why they do that. Okay, I prefer to introduce my students to the X, Y, Z notation right from the beginning. So here you go. Let's do this example here, right? By the way, let me write that down as well, right? Remember that I told you that those unit vectors, you know, those hat vectors have a magnitude of 1. So how do you write down the magnitude of a vector? Okay, we write the magnitude of a given vector is those two bars surrounding it. And in this specific case, this vector has a magnitude of 1. Those three vectors have a magnitude of 1, okay? So we are now going to find out, okay, example. Let's find out the magnitude, the length of this vector A. Let's do that. There's an example. We have this, you know, this arbitrary vector 2x plus 3y. How is it represented in the space? Okay, so there should be 2 units here along this direction and 3 units here along this direction. So I want to know what's the magnitude of the resulting vector A. The magnitude of the resulting vector A should be the length of this vector A. Okay, if the vector is 2 units along this direction and 3 units along this direction, you can find out the length of this vector by using the Pythagorean theorem. Can you picture that? So find the magnitude. Here you go. Here's the magnitude. That's how you find, right? Components x and components y are perpendicular to one another. Consequently, they form a right-angled triangle. AX and AY are the sides of a right-angled triangle. If you want to know the magnitude of A, you know, you just sum the square of the other 2 sides and take the square root. 9 plus 4 is 13, square root of 13. Okay, here you go. That's how you write it down. What about another one? Okay? That's one example. Find not the magnitude, but the angle. Here is find the magnitude, right? Of vector A. Next, find the angle of vector A with respect to the x-axis. Respect to the x-axis. Okay. So there's going to be another solution. Solution. So you have to illustrate this vector, right? So here you go. You have the angle theta. Let's see if I have it here. No, not this one. This one. Here you go. I want to know this angle theta. This vector has 2 units along this length and 3 units along this length. What is this angle here? Okay, so you go ahead. You know, you have, here you go. You have this a vector that forms a right angle triangle with the other 2 vectors. Okay, I'm gonna copy that and put down there in a simpler way. Here you go. I'm gonna take this guy out. We don't even need the x-axis, x and y-axis anymore. Okay, here you go. And you do know that the tangent of this angle is going to be the length of this side divided by the length of this other side, right? So going back to my solution of my problem, here you go. Solution. It can be also not only tangent, but you can also write down in terms of the sine, right? You know, AY, this length divided by this length is going to be also equal to sine. I did that in terms of sine instead of tangent. Okay. Cosine is that, tangent is that, right? And then you just go ahead, get your calculator there and find out what's the angle. Either the calculator or your Excel, right? I'm gonna do that for you. Here you go. It's 2/3, right? Here you go. Arc tangent 2 divided by 3. I'm getting 0.588 radians, and now I have to change that to degrees. Let me see here, degrees. Yeah. Excel always gives your angle in terms of radians, okay? And then when you change it, you get 33 degrees, 33.69 degrees, whether it's a arctangent, or we can also say, here you go, a sine, right? Arcsine, which is going to be what? Arcsine is going to be 3 over square root of 13, right? Square root of 13. A sine. Let me see what. Okay, I made a mistake here. Okay, let me see. There's something wrong here. Yeah, we got a different value here. Let me see what is that a sine. This arc was supposed to be the same as this one. Okay, so what mistake did I make? Let's see here. Oh yeah, the mistake was here, right? Oh, nobody picked that up, right? The mistake was here. I put 2/3. It's not 2/3. It's 3/2. Now, okay, now we got the right answer. See that? Nobody picked up on that, huh? We did for sine, we did for tangent, we can do for cosine as well. Either way, you know, I'm gonna put now a cosine. Instead of 3, I put 2, and instead of 2 is square root of 13. Let's see what we get. Same degrees in radians. Okay, we're supposed to get the same degrees in radians. So it's 56 degrees. What you see here is 56 degrees. Let's go there. Okay, 56 degrees. Oh, nope, that's not how we do it. The way you do it, like that. You go. You do theta equal to 56 degrees, right? Theta equal to 56 degrees. Now let's sum 2 vectors. Okay, let's sum 2 vectors. With vector A and vector B, right? And now we're going to use algebra, just like I mentioned before. Okay, so A plus B. I prefer to do, you know, let me, you know, I think it's better if I do from scratch, right? So you don't see, so you see the derivation in real time and you don't see the solution, right? So here you go, a plus b, right? A plus b. This is a, right? Next is gonna be b. Okay, what do we do next? We factor everything that x next to each other, and everything that's y next to each other as well. Next, first commute, right? And then you factor. Here you go. Now I'm going to do the factoring. Okay. Same thing here. Go. Okay. More. Here's 5. Here's 4. That's the resulting vector. And now if you want to, find the magnitude of a plus b, right? We do exactly what we did before. Here you go. Magnitude of a plus b, put between the is going to be what? Square root of 5 square plus 4 square, which is 25 plus 16. Okay, which is 41, right? Square root of 41. That's the magnitude. Yeah, square root of 41 and so on. Okay, let me erase that. You can subtract as well. Okay, I got the same value. Oh, you can get the angle as well. Here you go. I did the angle here as well. Tangent of theta is cy over cx. I call that the vector c. Okay. Vector c. Cy is 4, cx is 5. Take the arctangent of that, whatever it is, right? Here you go. Let's do that. Let's see what it is in Excel. 4/5, arctangent of 4/5. 4 divided by 5 is 38 degrees, 38.65 degrees. 38.65 degrees. Okay, that's the genetic equation that I did for you, right? Here you go. A plus b can be broken down as the sum of the x components plus the sum of the y components. The magnitude of a plus b is the square root of the sum of the x component square and the sum of the y component square. Okay. And now we have a quantitative way. Okay, now we also have a quantitative way of calculating the magnitude and the magnitude and the direction of a resulting vector. So recapping, right? Initially, I showed you how to determine how to picture a vector in the paper. Next, I showed how to actually calculate the magnitude, the sum between two vectors, the magnitude of a vector, the magnitude and direction of a vector, plus the sum of the of two vectors algebraically. So now you have this whole set of tools, graphical tools and algebraic tools to visualize and determine a vector resultant. And its direction. This is a summary that we have. Okay. And I showed to you, how to find the components of the vector, x and y components. Okay. And there is one more trick that you have to know. If two vectors are perpendicular to each other, we can find their summation using the Pythagorean theorem, right? We can find not their summation, their magnitude, the resulting. We can find the magnitude of their sum, right? Using the Pythagorean theorem. What if these two vectors are not perpendicular, right? Not perpendicular. Well, one way is to break down each vector and its components, right? And then use the Pythagorean theorem. That's one way. So there is one more little trick that you have to know. Another way is by using what we call the cosine law. Let's take a look at the cosine law. Cosine law can be derived. I'm presuming that you all know about trigonometry here, right? Can I hear something from you? Who knows trigonometry? Please just write down in the chat box. Yes, I know. Yes, I don't know. I don't know. It's been a few years. Okay. Want to hear more? Yes, I know. That's good. Yeah, and by the way, that's no, how do you call it? It's a prerequisite for this course, right? Okay, you did trig. Okay. Anybody else? Only 3 students have shared that with me. Want to hear from more? Okay, so okay, good. You did trigonometry. Okay, good. So let me know if you learned trigonometry or not. And what about vector? Have you seen vectors before, or you're seeing that for the first time? Okay, what about vector? Let me know if you learned trigonometry before. What about vectors? Have you seen vectors before? Or this is the first time? Okay, Mia didn't see it, right? Daisy saw. Is that right, Daisy? You saw vectors before? Okay. But vectors, I usually cover vectors here in this class, but I don't cover trigonometry. Okay, good. So, okay. Thank you all. Okay, and then there is this cosine law, okay? Another way of finding out the magnitude of a resulting vector, let two vectors that are not perpendicular to each other. Okay? Here you go. I'm going to write it down. This one, A and B. Two vectors A and B that are not perpendicular to each other. Let's see here. Okay. Find find the magnitude of the summation, this magnitude of their summation using the cosine law. Okay, here you go. Here is it's very easy to memorize that. It's very easy to memorize that, okay? Let me show you a quick way of memorizing it. Someone is ringing the bell here in my house. So here you go. Let's take a look here. Let me see. Okay, I'm going to use this as an illustration, okay? Let me see if I have a better illustration. No, I don't. I'm going to use this guy here as an illustration. Here you go. I don't need that. I don't need that. I don't need that. Okay. So those two vectors A and B are not perpendicular to each other, okay? And they are adding up. They're adding up. Let's see here. Sorry for the confusion here. I'm going to get this one here. I need this one. They are adding up, and the result is vector C. Okay, the result is vector C. This angle here is theta. Okay. There is a theorem, they call it a law, but in reality it's a theorem, okay? That relates this side with the other two. And it's very easy to memorize because it's very similar to the Pythagorean theorem. It's not the same, it's because the cosine law is more generic, okay? So here, this angle here, I'm gonna call beta because it's opposite to the letter B. It's opposite to the side B. This other angle here, I'm gonna call it the angle alpha because it's opposite to the side A, okay? Alpha, beta, gamma are the letters A, B, C of the Greek alphabet. Here you go, it's gonna be alpha. And finally, it's very convenient, one more here, and then this angle here that's opposite to side C, I'm gonna call it the angle gamma. Make sense? Gamma, like that. Alpha, beta, gamma. Alpha opposite to A, beta opposite to B, and gamma opposite to C. Okay? Don't forget that theta, right, is this angle right here. This angle right here. The angle is the horizontal. In the cosine law, we use the angles here of the vertex of our triangle instead. Here you go. How do you memorize that? Memorize it in the following way. I'm going to put it side by side. So even better, I'm going to copy it and paste there in my notes so you can see it in real time. Snipping tool, here we go. Okay, let's put there in this one. Okay, here you go. We shouldn't come in. Okay, so here you go. Even better, instead of writing down that square root, I'm gonna put c square here and take everything out. Here's the cosine law. I'm not gonna prove that. I'm gonna just display it to you so you can memorize. It's not difficult to memorize. Okay, this side square is equal to this side square plus this side square. That's what you have here in the first step. What you see here is nothing but the Pythagorean theorem, right? But the Pythagorean theorem applies only if the angle gamma is 90 degrees. For this reason that we must have this correction that you see here. And this correction is going to always be a negative sign twice the magnitude of A, magnitude of B, which is the length of A, length of B, times the cosine of this angle. Can you picture that? It applies, a similar relation applies for the other sides, okay? If C, magnitude of C squared is equal to that, magnitude of A squared, you know, is going to be magnitude of B squared plus magnitude of C squared. Make sense? Minus 2 magnitude of B, magnitude of C, and now the angle is no longer going to be gamma. The angle is going to be that angle opposite to the side A, right? Here's the angle opposite to the side C. Here's the angle opposite to the side A, so it should be alpha. And then a similar relation applies for the magnitude of B. Okay, I'm not even going to bother. You go like that. What changes again? Is going to be the angle beta, right? Length, side, opposite angle to the side. Side, opposite angle to the side, right? Side C, opposite angle to the side C, gamma. Side A, opposite angle to the side A, angle alpha. Side B, opposite angle to the side B, angle beta. Can you memorize that? If you display like that, it becomes easy to memorize, right? Okay. So it's 10:45 right now. Let's let's apply the cosine law. It's not a law, okay? That's why I write that down. I usually write it down is between quotes. It's actually a theorem. It's not a law. It's a theorem. There's cosine law and there's the sine law, right? They're not laws. They're theorems. People give it, wrong names for the right things. Even in math and physics, they do that. Okay, so you gotta watch out for. And those mistakes keep on propagating throughout the literature, and nobody bothers to correct it, to change it. Okay, so let's apply the cosine law now to that same problem that we did before. So here we go. A and B, right? I'm going to illustrate those two vectors, A and B. Right? Let's illustrate those two vectors, A and B. A is what? 2x, right? 2x plus 3y, yeah? That's what we have here. Yeah, it looks like 2x in this direction, right? And 3y in this direction. And then B is what? 3 units to the in the horizontal direction and 1 unit in the vertical direction, right? We do not know those angles, right? But if you find out those angles, we will be able to solve the problem. Okay. I'll leave that for an exercise, but if you do everything right, okay, you will find the angles that we have. And once you find the angles, you will know how to calculate the magnitude of C, okay? That's what we have here. Let's see. Okay. Oh, here you go. I have the. I had already written that. We'll see. Yeah. Okay. I wrote that right now. Okay. And now what we did up to now was to introduce you to the tools, to a new type of tool, to a new mathematical tool that we call vectors. Number is a mathematical tool, vector is a mathematical tool. Okay. Now, what we're going to do now? Now we will apply this mathematical tool, not these, but this mathematical tool to actual physical circumstances, right? To actual physical problems. Circumstances, yeah, it's slash problems. Like I said before, you know, mass, length, mass, and time are scalar parameters, even better, quantities. But I also told you that position and force are vectorial parameters. In this case, I'm not going to call them quantities. I'm going to call them definitions, right? To ensure that they stay consistent what I did before. Okay, so the question that you have to pose now, you know, are there any other vectorial definitions in physics? That's the question you have to pose to yourself. And the answer is yes. Right? By the same token, there are several other scalar quantities in physics as well, right? I already told you that distance traveled and speed are scalar quantities. And How do you find out? How do you find out which parameters are vectorial and scalars? Which parameters are vectorial and which are scalars? Okay, how do you find that out? How you find that out? You find that out from their definition. Definition. Okay? You already know that position and force are vectors. Consequently, anything else that is defined in terms of these definitions, these primary definitions, comma, should be vectors as well. Okay, make sense? That's how you find out. All you have to do is to memorize the quantities. The basic quantities are scalar. The primary definitions are vectors. If I come up and define something else in terms of the basic definitions, it means that this new something else is going to be a vector. On the other hand, if I define a new quantity in terms of the basic quantities, you can be rested assured that this new quantity is going to be a scalar. Okay, just like delta t, right? Delta t is defined in terms of t final and t initial, so it must be a scalar. So we just go back to what we did before in one-dimensional physics, one-dimensional motion, right? Let's go back to one-dimensional motion. Here you go. We have, that's page 46. Remind me that, okay? Page 46. We're gonna go back to what we did in one dimension, and then we go back to page 46. We're gonna have our break very soon. Bear with me. Here you go. Let's see. Oh, right in here, right? Remember that? Remember that? I'm going to copy only up to here, and then we're going to go back to page 46. When we were doing one-dimensional motion, I didn't bother defining vectors because it's just one-dimensional motion, right? One-dimensional motion doesn't require vectorial treatment. But now that we are going to start talking about two-dimensional motion, we need to worry about the vectorial behavior or certain definition that we have in physics. Okay, here you go. Vector. And by the way, there's one missing here. You know, for some reason I didn't put it. Then we have what else? Displacement. Okay. Recall that displacement is final position minus initial position, right? I will save that for a later time. We go. Oh, this one. Let's start with this displacement first. Okay. One-dimensional definition. One-dimensional definition of displacement. Okay. So here we go. Get that my vector here, my equation here, not vector, but my equation here. Okay, delta x is equal to x final minus x initial, right? That oh, x initial. Okay. What about the two-dimensional definition of displacement? Okay. the two-dimensional definition of displacement, we are going to write down in terms of the initial position. And by the way, the initial, the two-dimensional definition of displacement, we write down not delta x, but we write delta r. Okay. And here, what you're going to have is going to be the final position, RF, minus the initial position. I'm going to illustrate that in PowerPoint, how it looks like. It's 1056. Let's see here. Okay, so here you go. Here is the XY plane of motion. Now remember, where the particle is no longer constrained to the X, to a single one-dimensional motion, right? To a single dimension of motion. Now the particle is constrained to the X and Y axis. You can move up and down here, not just along the X axis, not just along the Y axis, right? So let's say, I'm gonna make it even simpler than that. We start with the X and Y axis. Before we even start with the X and Y axis, we started with the X axis, right? X axis, and then we added the Y axis to illustrate two-dimensional motion. And now we have this particle that's moving in the most generic sense in this XY plane. Okay. I'm going to illustrate what is the initial position vector of this particle is all about. So let's say at time t equal to 0 or t naught, the particle is right here at this spot. I'm going to make it even simpler than that so you can play the movie accordingly, right? Let's say the particle is at this point here, right? And this point has coordinates x naught, y naught. And this coordinate x naught, y naught can be represented also by a vector, an arrow that goes from the origin of the coordinate system to the point where it is. This arrow, this vector, I give it a name, I call R naught. I'm going to bold face it so everything is consistent here. Okay. And don't forget, this particle is moving along this path here in the XY plane. At time t equal to 0, at time t naught, an initial instant of time, it is here. Later on, it's going to be somewhere along this path. Okay. At time t equal to t2, let's say, it is elsewhere. And I'm going to elaborate a little bit more, right? Again, later on, the particle is going to be there at that spot, right? And at that spot, we can represent that position by another vector, an arrow, by the way, that we call RF. I don't need that. Yeah, you need that. Let's play the movie again. Here you go. In order for you to understand displacement in two dimension, you have to go through this exercise. You have to go through this exercise to visualize it. Okay, we start with the x-axis. We add the y-axis because it's two-dimensional motion, and then we, illustrate a generic path along the x-y axis, a curve like that. And we place a particle at the initial instant of time at this spot, illustrate its coordinates, x naught, y naught. This coordinate x naught, y naught can also be illustrated by a vector position, which is the initial vector position. Later on, this particle, it's at another position. And by the way, there's something else missing here, right? what I'm gonna do. Okay, and what I'm gonna do here, let's see here. Yeah, I'm gonna do exactly what I did before. Okay, yeah, I'm gonna put this guy here. This guy there, right? Okay, now I'm gonna put, yeah, I changed the notation, right? Let's put it here. It's supposed to be T naught. Let me fix that. Yeah, I changed the notation. I was not supposed to change the notation. Yeah, T naught. Yeah, I put T1 here, right? And this one now is gonna be T1. Good. And now, oh, put T1 here. This one's gonna be X1, Y1. Make it consistent. Oh, this one is T naught. Oh gosh. Let me put everything T naught so you don't have any of this type of problem again. Here you go, T naught. Yeah, T1, huh? Everything there. Well, I'm gonna fix that, but I don't want to disclose everything, to you. Otherwise, here, I'm just fixing, right? Here you go. Now this one's gonna be T1. I'll call that X1, Y1. And then instead of calling XY, Y1, the coordinate XY, X1, Y1, I just say, look, we have this vector position RF, final position. Okay. So the displacement vector in this illustration is going to be the vector that goes from the initial position to the final position. Make sense? Okay. Recall that here is RF minus R naught, right? So if you sum R naught with delta R, you are going to get RF definitely, because this thing here is, you know, R. It doesn't like it. Let me see if it allows me to do that. Yeah, he doesn't let me do that. Too bad. Yeah, I'll have to copy from elsewhere. Let me copy from, I'll leave this way. I'll leave this way. Okay. So just say R naught plus delta R is going to be RF. Okay. So I'll do that for you. Okay. I'll prove that for you here, right in here. R naught R naught plus delta R is going to be what? R naught plus delta R is going to be what? All you got to do is to sum, is to put an R naught here in front, right? And look what happens. These R naught cancel out with the other R naught, and it is indeed RF. So our notation is correct, it's consistent. Right? R naught plus delta R is indeed RF. Okay, that's one way of looking at that. It's 10:11:04. Let's take a break right now, and then we continue in the next 15 minutes. Okay, any questions about that? Okay, another break. Let us take another break. Let us take another break till 11:20 a.m. Okay. So there is no questions. I'll see you in 15 minutes. Okay, I'm back here. So you can picture, right, that this guy here is delta R, right? There's another way to look at that. How you can picture delta R, which other way you can picture delta R, right? I'm gonna show you another way how you are capable of picturing delta R. Remember, delta R is RF minus R naught, right? Make sense? Here you go. I'm going to illustrate R naught for you here. Size and position, that's not this one. Format shape, here you go. I'm gonna illustrate R minus R naught for you, here you go. That's what you see right here is minus R naught, right?
Can you share your screen, Professor?
Oh yeah, thank you, thank you.
Yep.
Oh, sometimes I forget about that. Thank you. Let me go. Here you go. Now we have it. Right? Let me put it. I don't like this arrow with this. I prefer this arrow here. See that? It's far easier to see than the other one. Here you go. Either this arrow or this. Let me change those arrows. Okay. What you see right in here is the minus R naught vector, right? And if you sum minus R naught with plus RF, you end up getting delta R, right? That's another way of picturing the vector delta R. So everything goes back to those definitions that we saw before, right? To the vector concepts that we saw before. So here you go. Let's play the movie again, right? This is no Avengers movie, but it is a movie nonetheless, right? So here you go. We start with the x-axis, the Cartesian coordinate axis. We add the y-axis. Why am I doing that? Because we are illustrating motion in 2 dimensions now. So I need to know the x position and the y position of my particle. Here is the path of the particle, a very generic path. We are going to study more specific paths for particles. But this one, that's how we introduce to the students, the most generic one that you can picture. So, and then we put the particle at the given instant of time along this line. This particle is a position x naught, y naught. That should be known because we have this curve here. I illustrated this curve, and this position, this coordinate x naught, y naught can also be represented by a vector, right? A vector that I call R naught. Okay, and then at a later instant of time, t1, the particle moved elsewhere. Time t1. And this position of the particle can be illustrated by the coordinates x1, y1, which, by the way, can also be illustrated by a vector. This vector I called final position vector. And if we study very carefully, you will convince yourself that the vector displacement is going to be this one that I'm illustrating here in this graph. Okay, that's the vector displacement, which is RF minus R naught. Here you go. Yeah, another illustration, right? RF minus R naught. Delta R is RF minus R naught, or if you prefer, delta R is minus R naught plus RF. That's how we find out whether a new definition is a vector or not. It is by its definition itself. If it is if its definition is related to an original vector. Okay, what else we have here? Okay. Oh yeah, here you go. Here's the, how do you call it? Here is the, you saw, what you saw here was the tail to head method, right? And what you have here is the parallelogram method, right? R naught plus delta R is RF. That's what you have here. Now, what else? What else can you remember that average velocity is delta R over delta T, right? Is the vector delta R divided by a scalar. Because the average velocity is defined, is directly proportional to the vector displacement, the average velocity vector will point in the same direction as the displacement vector, right? Here you go, I'm gonna move it here. See, they're pointing in the same direction. I made sure that they point, just there is just a small, difference here, right? Now they're very parallel to each other. Remember, average velocity is just delta R over delta T. Let's write that down in my notes. Okay, two-dimensional definition of displacement. And now that's where we get to the point where we are talking about the average velocity. They call that the average velocity is, I don't like, sometimes this software, they start to misbehave, I don't know why they do that. Let's see. What's going on here? It's not, okay, I know why. Here you go. Now it should work. Yeah, I finally discovered why is that. Let's do that again. You go back. Good. Equal to what? Delta R divided by the scalar delta T, right? Because it's one vector divided by the scalar, then the average velocity vector is, this implies, we go. This implies that the average velocity vector is parallel. You know the symbol of parallel? Oh, I hate that. It seems I'm dividing something here. Oh man. Let me see if they have, nope. Yeah, it doesn't like it. It seems I'm dividing it. Let me see if I have the parallel symbol here. No, they don't have the parallel symbol. Okay, so I'm gonna write down parallel to delta R. That's from the very definition of delta R. Okay. Now the next thing that you are supposed to picture is the instantaneous velocity vector. And the instantaneous velocity vector has a very nice interpretation, graphical interpretation. Am I recording, by the way? Yeah, am I recording? Yeah, I am recording. Good. So here you go. How do we find out the graphical interpretation of the instantaneous velocity? Okay, we use the definition that we already know, right, about instantaneous velocity. Let me see if I have all the slides. No, I don't have all the slides. I'll have to do that on my own. Okay, here you go. Instantaneous velocity vector is what? Is is the limit of the average velocity as delta t goes to 0. Limit. Here you go. I'll put that here. I'll use it. Thank you. And we are going to be able to see it. Okay, I'll put delta t here. Delta t not to infinity, but going to 0. And okay. So we are going to do exactly what this thing is illustrated. Let me see if I have it here. I don't have it, unfortunately. Huh? Let me see. Yeah, I don't have it. I have to create that from scratch. So let's go. Hopefully I have a good, okay. So we start with this average velocity and we want to find the instantaneous velocity. Let's say I want to find out the instantaneous velocity at this point here at T0, okay? So what do? I start decreasing my delta T, okay? So instead of this, by decreasing the delta T, I mean I start by making T2 closer and closer, oh gosh, to the previous one. Go, yeah, right? When I do that, you know, my delta R is gonna shrink as well. And my average velocity is gonna change as we do that. Here you go. See, not only the magnitude of the average velocity is gonna change, but also the direction as well. Okay, I'm doing delta T going to 0 little by little. And let's watch out what happens to this average velocity vector. Okay, here you go. One more. I'm gonna shrink my delta T again. Here you go. I'm gonna make it closer and closer. It's not gonna be T2, right? It's gonna be T1. Why did I put T2 there? Okay, it's gonna be 2 primes T1. And oh, by the way, I should have put this point here. That's an exercise that we do to, and now I'm not gonna put the RF there, otherwise it's gonna become too busy, my graph, right? So what happens to the average velocity, right? The average velocity again changes direction and maybe changes intensity as well, changes the length as well. We go one more step, okay? I'm making my delta T goes to 0. Here you go. Now delta T goes right here. Delta R, my position, my particle, position of my particle. Okay, here you go. Now it's gonna be T3 prime 1, right? And again, notice that my velocity, average velocity, the average velocity is not decreasing necessarily, okay? Delta R is decreasing, yes, but the average velocity is not decreasing necessarily. Why is that? Because average velocity is delta R over delta T. If delta R is decreasing, delta T is also decreasing, right? Maybe, you know, the velocity is increasing. We do not know, okay? But the direction is definitely changing in this problem of ours. The direction is definitely changing, okay? We go another step, you do that until delta T goes to 0. Okay, so that's gonna be the next one, the next point for delta T going to 0. I'm not gonna change the notation anymore of the delta of the T1. I'm gonna leave like that. Otherwise, and what happens to my average velocity? My average velocity, the direction of the average velocity is the same direction as the delta R, right? But the magnitude is not necessarily the same. Eventually, when this delta R becomes 0, something interesting happens, okay? When delta R becomes 0, in the limit, right, of delta r going to 0. When delta r goes to 0, this guy becomes, this average velocity becomes instantaneous velocity. And it's possible to prove mathematically, okay, the average velocity becomes the instantaneous velocity, right? And it's possible to prove that the direction of the average of the instantaneous velocity becomes tangent to the point, to the path of the curve. Okay, it's possible to prove that mathematically, yeah, but that's how we do it in this course. It's possible to prove it using calculus, okay? But that's a little piece of information that's very easy to remember, right? When delta r goes to 0, instantaneous velocity is tangent to the path of the particle. I'm going to write that down for you. Let's play the movie again. 11:38, we still have enough time. Here we go. We start with this average velocity, delta r, right? We start shrinking my delta r. I shrink, not only I shrink the delta r, but I also shrink the t, right? The instant of time t. The instant, not the instant of time t, I shrink the delta t, okay? Delta t, and because delta t is going to 0 in conjunction, simultaneously, in synchrony with delta r, the average velocity in the limit is still going to be a finite number. The average velocity, which is going to be tending towards the instantaneous velocity, is still going to be a finite number, okay? And that's what's happening here. Here you go. Eventually, when delta r goes to 0, the instantaneous velocity becomes tangent to the path of the particle, okay? And I'm going to correct all those T2s here, supposed to be T1, right? So you don't get confused here. Here you go. T1, T1. I don't want the number 1 to be italicized. Here you go. T1, next one here. T1, T1. That's the method of induction. We call that the method of induction. We don't completely prove it, but we can be induced that exactly what happens. We go T1. Yeah, I'm not going to put the prime in there because the notation is going to become too big, right? T1, T1, you know, I'm just removing the cumbersomeness of the notation. Next. Okay. We are going to write that down here in my notes. As delta t goes to 0, as delta t goes to 0, the direction of the instantaneous velocity ends up coinciding with the tangent, with a direction that is tangent to the path of the particle. Okay. And you go, I will add that so you can have the full picture of what we are doing. We can benefit from the full picture of how we are doing, right? Here you go. Position, delta R, instantaneous velocity. Is a direction that's tangent to the path of the particle. 1142. So what about the average? Oh, let's go. Let's illustrate the different velocity vectors along this path, right? Here you go. Here you go. I'm gonna just illustrate the velocity vector. I didn't get to the acceleration yet. Let's eliminate those acceleration vectors here. You don't need that yet. Oh, what did I do here? Yeah, here you go. That's V2, right? Okay, so here you go. Here's just an illustration of how the velocity vector of the particle looks like. At this instant of time, is going to be somewhere in this direction because it's tangent to the path. I can only state the direction of the velocity vector. I cannot say anything about the magnitude of this velocity vector under this treatment, okay? I can only state that the velocity vector is tangent to the path of the particle, nothing else, okay? Here you go. Here's another vector, velocity tangent to the particle. Go, I'll call that V4 because we have V3 down there, right? That's gonna be V4. This other one is gonna be V3. Okay, I don't need that yet because we didn't get that. Let's see, someone is chatting, okay. Any questions? Now, what's the next step? Okay, the next step is exactly what we did before for one-dimensional motion, right? We're going to have, eventually I'm going to talk about the equations of motion, okay? A constant velocity. Let's skip that for now, okay? What I want to do now is the acceleration. And how it looks like in the XY axis, okay? Now we're going to talk about the average acceleration. Average acceleration vector has the same one-dimensional definition. Okay, and what's that gonna be? Here you go. Average acceleration vector is going to be delta V over delta T. So what does it mean? It means that average acceleration is parallel to delta V. Okay, then we're going to talk about the instantaneous acceleration, but let's picture how it looks like in this graph. So here you go. We have V1 and V2, right? Between V1 and V2, we are going to have this average acceleration. V2 minus V1 divided by delta T, right? So did I put that? I'm going to do even better. Here you go. I'm going to write that down. Delta V2 minus V1. It's a vector. V2 minus V1 over delta T. Average acceleration vector is parallel to delta V. Let's see if it's parallel or not. Okay. Let's see if it's parallel or not. Oh, here you go. Here's V2. Okay, here you go. I'm going to transport. Yeah, I put it is V2. This one is V1 minus V1, right? Is it minus V1? Yeah, it is minus V1. We sum those two vectors. We sum V2 with minus V1. We get delta V. See that? That's the resulting delta V, which, by the way, is going to be parallel to the average acceleration vector. Is this guy parallel to this one? Yeah, it is. So the average acceleration vector, is going to point somewhat like that. We can do the same thing for the other average accelerations between V2 and V3, for instance, right? There will be another average. Here you go, V2 and V3 is here. We're going to have another average acceleration vector somewhere around here. Okay, between V3 and V4, we're going to have another, let's say, average acceleration vector somewhere around here. Depends, somewhere like right in here. In this case, I can tell you there's going to be a very small value. Okay, but there is a very important point to take home. Okay, the average acceleration is going to usually point towards the center of the concavity of a pass. Okay, do you see here we have a concavity here, and this average acceleration vector is pointing towards the center of this concavity. This is no coincidence. Okay, this is the actual result. Here too we have a concavity here. Okay, and the average acceleration is pointing towards the center of the concavity, and so on. Okay, there's a very important piece of information to take home. I'm going to write it down for you. Both the average acceleration vector and the average acceleration and instantaneous acceleration vectors, both the average and the instantaneous acceleration vectors point towards the center of the concavity of the path of our particle. Okay. And the instantaneous acceleration vector, you should already know, right? Here you go. I'm gonna take this one, write that down right in here. Instantaneous acceleration vector. Limit as delta t goes to 0 of the average acceleration vector, delta v over delta t. Okay, so you may perfectly have in the exam a question. I go ahead and look, I give a path, a general path of a particle, and I tell you which direction that acceleration points, right? Right now, at this point, the instantaneous acceleration vector is going to point in this direction. At this other point here, the instantaneous acceleration vector is going to point in this direction towards the center of the concavity. Here is towards this side. Here is towards this side, and so on. Okay? That's what you have to know. And what else can we talk about? Okay, so I can erase this part here. What we're going to see next is going to be types of motion in 2 dimensions. So far, what you have seen here is just a genetic description of how those vectors, instantaneous velocity, displacement vectors, instantaneous velocity vector, average acceleration vector, right? Instantaneous acceleration vector, how they look like in the plane. Okay, so but let's summarize. Here you go. Summarize. 1, given a genetic path in the XY plane, genetic path of a particle in the XY plane, okay, comma, we have the following, A, the instantaneous velocity vector will point in a direction tangent to the path, the instantaneous acceleration vector will point in a direction towards the center of the concavity of the path of the particle. Okay, that's what you have to know. So let's go back here to my drawing. There's one more thing that I want to yeah, here you go. I'm going to show you that as well. Notice that, notice this, the illustration of this acceleration vector here at this point, right? Towards the center of the concavity. This one is towards the center of the concavity. This one is towards the center of the concavity. We can explore that even more, okay? We can recognize that this instantaneous acceleration vector has a component that's tangent to the direction of motion of the particle and also normal to the direction of motion of the particle. Can you picture that? Let's go back there. If this direction here is tangent, you can see that your acceleration vector has a component that is also tangent. Okay? I'm going to put that in the next figure so you can picture it better. Oh, very unfortunate. Here you go. And I'm going to send that to the back. Here you go. Good. We have an acceleration vector that's tangent to the path. And by the way, it's contrary to the direction of the velocity vector. Do you see that? And we have a component that's also perpendicular right here. I can draw the perpendicular symbol. Here you go. Here's this perpendicular symbol. Black, and we're going to fill it with white, right? Perpendicular symbol. Whoa, rotate it a little bit. Yes, okay, did I get it perpendicular? Yeah, it looks like I did. Yeah. Shrink a little bit, right? Here's the symbol of perpendicular. Tangent component of the acceleration, normal component of this acceleration. We don't call it perpendicular component of acceleration. No, we call it normal component of the acceleration. We call it normal because the normal direction is a direction that makes an angle of 90 degrees with the tangent, okay? That's what the definition of normal is, okay? Note C. I'm going to write that down here for you. Note C that a given instantaneous acceleration vector may, in general, okay, in general, has a tangential component and a normal component. Normal means a direction that is perpendicular to the tangential direction. Okay. So going back here. Now, because this tangential component of the acceleration is going against the velocity vector, what does it mean? It means that a little bit later on, this velocity vector is going to shrink. It's going to shrink in length, okay? Will shrink indeed. So here you go. If the velocity vector is this long at this spot, it means that a little bit later, this velocity vector is going to be a little bit shorter because the acceleration is acting in this vector in the opposite direction. I'll call this one the V1 prime. Okay. Good. V1 prime. Now, Take a look at this other acceleration vector at another instant of time, Notice that the net acceleration vector is completely perpendicular to this velocity vector. What does it mean? Well, it means that this velocity is not going to increase nor decrease. That's what it means. Okay, it's not going to increase in length nor decrease in length. Here we have a situation similar to this one. The acceleration vector has a tangential component that goes against the velocity vector. It means that this velocity a little bit later is going to shrink. But if this acceleration vector were in this direction here, a little bit later on, this v3 velocity vector would increase, okay? Because it has a component in the same direction as the velocity. So 11:58 right now. So any questions about that? I think we can stop. And let me see if you have any questions in the chat box. A quiz? No, we're not taking a quiz today, Donia. We're not taking a quiz today, okay?
Thank you.
And it's already 12 noon, almost 12 noon, right? And those are ideas that you have to keep in mind. Next class, we're going to look at specifically, we're going to look at specific types of motion in 2 dimensions. Okay, we're going to look at the projectile motion, and projectile motion is like that, is here you go, an object. Here you go. Let me stop sharing the screen. Here you go. Projectile motion is this type of motion here. If we study this motion mathematically, you're going to find out that the path that this projectile moves in the 2-dimensional space is going to be a parabolic one, okay? Good, so we can stop right now. And if you have any questions, you can stay for office hours. And I will see you on Wednesday when we are going to have our first exam. Okay, and you should expect something like 15 to 20 questions in the exam. I'll put down in my notes here. Here you go. Expect. I'll share the notes here with you. Go share the screen. Expect between. Expect anything between 15 to 20 questions in the exam, multiple choice, and numerical answers. Numerical answers. Okay. Okay, so I see you on Wednesday. Okay. Okay.